As we've been looking at atoms, we've looked at how they form ions, different types of molecules, how they can be put together in both ionic and molecular compounds. But things aren't quite as simple as one or the other or being black and white. There's actually a bit of a bonding spectrum between ionic and covalent that we're going to look at today. So a quick reminder that electronegativity, okay, which is one of the periodic trends we've looked at, is the ability of an atom to attract electrons. Okay, and remember that each element has a specific electronegativity except for the noble gases. So the noble gases are 0. They do not want another electron. So in terms of types of bonds, we've talked about ionic and covalent, but really we have ionic, and then covalent is broken down into polar covalent and non-polar covalent. Okay, polar, think of the word pole, like the North Pole and the South Pole of the Earth. So to have two poles is to have two different ends of something. So a polar covalent bond is when you have uneven sharing of the electrons in the bond, the bonding pair. And non-polar covalent means that it's completely even. Okay, so you can determine if a bond is polar covalent or non-polar covalent by looking up on the periodic table the electronegativities of the two atoms involved in the bond. If the electronegativities are the same or very close, a non-polar covalent bond forms, okay, where the electrons are shared evenly, okay, between the two atoms involved in the bond. If the electronegativities are quite different, a polar covalent bond forms, where the electrons are not shared evenly between the two atoms in the bond. Okay, and the bigger the difference in electronegativity that you see between those two atoms, the more polar the bond is. So remember we said this was a spectrum, it's not one or the other. So the bigger the difference, okay, the more polar the bond is. Below you'll see a diagram of a periodic table showing the electronegativities of each element. You'll note that there's nothing written in for the noble gases. Okay, and it has a specific number for each element. This periodic table of electronegativities you'll find on the back of your regular periodic table, and you will always have access to that for tests and quizzes and the exam. So what this means is we can actually check individual elements and see what the difference is in the electronegativity between those two elements. 3 special elements of note, okay, would be nitrogen, oxygen, and fluorine, because they have by far the highest electronegativity of all of the elements on the periodic table. If we do a quick reminder of our periodic trends, electronegativity increases as you go up and to the right, excluding the noble gases. So these are going to be your highest. If you look at the numbers down here, are your lowest. And we're going to use this to be able to measure the difference between elements to decide what type of bond they are. Keep that close by, and we'll refer back to it in a moment. Here's our spectrum of ionic to covalent bonds. When we're looking at the difference in electronegativity between two elements, we can measure that difference and then use the difference to figure out where on the spectrum it falls. So non-polar covalent bonds are over here between 0 and 0.5 as a difference. Okay, polar covalent bonds actually overlap a little bit with ionic bonds. So this 2.1 isn't quite a hard line. It's more like 2.1 to 1.7. And so you get a little bit of overlap between these two. And when you're trying to decide if something should be polar covalent or ionic, ionic should always have a metal. Okay, so ionic bonds have a metal in them. Polar covalent, if it's up to 2.1, it can still be polar covalent, okay, but it would be all nonmetals only, versus ionic would have a metal, and they can be as low as 1.7. So let's actually see what this looks like. We're gonna look at 3 different examples between carbon and oxygen, sodium and chlorine, and then 2 oxygens. So carbon and oxygen, first thing we're gonna look up the electronegativity of carbon. So En is the short form for electronegativity of carbon. If we look back, is 2.5. So we've got 2.5. The electronegativity of oxygen over here is 3.5. So when we're calculating the difference, we take the difference, so delta En, that represents the difference between the electronegativities, is 3.5 minus 2.5 gives us 1.0. Therefore, if we look at 1.0 falls in this range, this would be a polar covalent bond between carbon and oxygen. When you're doing the calculating the difference, always take the larger number and subtract the smaller number. It doesn't really matter. If you do it the other way around, you'll get a negative number, which it doesn't matter. It's the magnitude of the number that gives us our answer, not the direction, whether it's positive or negative. But if you don't like looking at negative numbers, just always start with the larger number minus the smaller number, and then you'll get a positive integer. If we look at the bond between sodium and chlorine, the electronegativity of sodium, looking at our table, is 1. So 1.0. Chlorine, the electronegativity of chlorine here is 2.9. So the difference, delta En, is 2.9 minus 1.0, which gives us a total difference of 1.9. Okay, we've also know we've got a metal and a non-metal. So this falls in that sort of little gray area here, but because we've got a metal and a non-metal, we know that this is going to be an ionic bond. The last example here is looking at oxygen forming a bond with another oxygen. So this would be like an O2 molecule. The electronegativity of oxygen we already looked up, and it was 3.5. So the difference in electronegativity between these two elements is going to be 3.5 minus 3.5 because they're the same, which is going to give us a difference of 0, which means that it's going to be a non-polar covalent bond. So small difference, non-polar covalent, larger difference, polar covalent, okay, and when it's really big difference, we get an ionic bond. Now there's a few different ways that we write this down and show it in diagram form. So when a polar covalent bond forms, the electrons are still shared, but they're not shared evenly. The side of the molecule that electrons are attracted to becomes slightly negative. So the more electronegative element is going to pull the electrons close. Remember, electronegativity is an atom's ability to attract electrons. So it's going to pull the electrons close to that side, and it's going to give that half, or that side of the bond, negative charge, or a slightly negative charge. The other side is going to become slightly positively charged. This is because with the lack of electrons being near that side, the protons in the nucleus are not being completely evened out by the electrons, so you have a slightly positive half to that bond. The difference in charge within a molecule is called a dipole moment. So dipole, di meaning two, pole is like the two poles of the earth, like we said earlier, like South Pole and North Pole, two different ends. So two ends. We write this dipole notation a couple of ways. So the first one is we use lowercase delta with a little minus sign. So it kind of looks like an unfinished figure eight is lowercase delta. Some people draw it also like this kind of, or like a musical note. Is used to show the partially negative side, and we show delta positive to show the partially positive side of a single bond. So this is when we have a single bond. An example here is we look at the carbon-hydrogen bond. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. So the hydrogen side is less, the carbon side is more, which means that the electrons in this bond aren't going to be shared evenly. They're going to spend more time towards the carbon side, giving the carbon side a slightly negative charge, and the hydrogen side a slightly positive charge. So we can show, these are called partial charges, okay? And partial charges are used for showing single bonds. Okay, then we used a crossed arrow that looks like this to show the overall dipole in a molecule, okay, where this is the positive half that is crossed at the end and looks like a plus sign, and the negative half is the arrow side. So when we look at the molecule of oxygen here, oxygen and hydrogen, so we've got water, the electronegativity of oxygen is 3.5, electronegativity of hydrogen is 2.1. So when we compare those numbers, we're going to see that the electrons in these two bonds are going to be spending more time towards the oxygen than the hydrogen, giving this side the slightly negative part, and the hydrogen ends the slightly positive charge. So that is our partial charges, and we can use that to determine an overall dipole for the molecule, which you can write off to the side as being like that, like you would show the direction, or you can draw it right on your molecule, which I'm going to use a highlighter just to make it easier to see. So this is my positive end, and the oxygen is my negative end. We're going to do a short demonstration in class looking at what this means for the properties of these molecules, but for now, this is it.